Here from ADSUL'S Technical Campus, Chas, Ahmednagar. Last lecture we have discussed about ideal transformer on no load. We discussed there the ideal transformer having don't have any kind of losses, and while we checking the performance of ideal transformer on no load, we neglect all type of losses. So but in this case we have to consider the losses. Okay, let's start. Practical transformer on no load. Practical transformer on no load. In case of ideal transformer, we neglect losses, but in case of practical transformer on no load condition, we have to consider all the losses like windage losses, core losses, or friction loss, or hysteresis losses, or iron losses. Okay, in case of practical transformer, we have to consider the all kind of losses. Okay, for that we have to draw here simple circuit diagram. Last lecture we already draw this diagram. Here we will also draw this diagram. First of all, I will draw here magnetic core. This is the magnetic core, named magnetic core. After that, we have to draw here primary winding. After that, we have to draw secondary winding or secondary side of the transformer. This transformer is practical transformer on no load. So keep secondary side of the secondary winding open. Okay, and this primary winding having N1 number of turns, and this winding having N2 number of turns. We connect here primary winding with single phase AC supply, and the voltage across the primary winding is named as V1. So let's start the process. In this process, when AC supply is applying to the primary side of the transformer with supply voltage V1 to the primary side of the transformer, then the primary current will start flowing to the primary winding of the transformer. This primary current set up magnetic fluxes phi in the primary winding. It generates the primary fluxes phi. So we denote here flux phi. These fluxes further traveling from magnetic core to the secondary winding of the transformer, and this generated fluxes linked with the secondary winding of the transformer when as per the principle of mutual induction or the transformation principle, when the flux is linked with the secondary winding of the transformer, which also induces the EMF. Here EMF is induced, that is E2, and the EMF induced in the primary, because Faraday's law of electromagnetic induction is the E1. Okay, is the E1. When the primary supply voltage V1 is applied to the primary winding of the transformer, then the primary current starts flowing through the primary winding of the transformer. But this primary current generates, this primary current contains small amount of core and iron losses, because this transformer is electrical transformer and the condition is no load condition. Okay, means the primary voltage V1 generates the primary current, and this primary current supply which supplies small amount of copper and iron losses. Okay, then here load is not connected, so the no load current is denoted by I0. Okay, the no load current is denoted by I0. This I0 current means no load current. This I0 current has two components, IC and IM. This I0 current has two components. First is IC and second is IM. I0 is called no load current. I0 is called no load current. Then IC is the core component or active component or backfull component or backfull component. This IC is called core component. This IC is called core component or active component. Core component or active component or backfull component. Okay. After that, second component is IM. This IM is called as magnetizing component. This IM is called as magnetizing component. This magnetizing component is also called as reactive component. Okay. This component is also called as reactive component. IM is called as reactive component. Reactive component or magnetizing component. Reactive component or magnetizing component. Okay, the no load current component, the no load current having two components. First is IC, second is IM. IC is active component or core loss component or backfull component or core component. Okay, core component or core loss component. And after that, IM is the reactive component or magnetizing current component. Okay, so the flux phi, when we draw here a phasor diagram, now we draw here phasor diagram of electrical transformer on no load. Electrical transformer on no load. We draw here phasor diagram. To draw the phasor diagram, we consider a reference flux phi. Consider the reference is flux phi. We know that the flux phi the flux phi is always in phase with the magnetizing component. Okay, that means flux phi and the current Im, that is magnetizing current, is on same phase. Okay, flux phi and magnetizing current Im is on same phases. That means they are in phase with each other. So after that, V1 is in phase with the IC, and we know that flux phi, the winding is we know that the winding is inductive. That means V1 is lagged phi by 90 degree. Here is V1, and this V1 and IC, okay, this V1 and IC are in phase with each other. That means we draw here IC. We draw here IC, and the resultant of these two components is a I0. Is I0, that is no load current component. Okay, the resultant of these two is I0, and the I0 make angle with the VM is phi 0 angle. Is phi 0 angle. This I0 makes angle with the V1 by phi 0. That means I0 lag V1 by angle phi 0, where phi 0 is the no load phase angle. This phi 0 is called as this phi 0 is called no load angle. This phi 0 is called no load phase angle. No load phase angle, and the cos of phi 0 is called no load power factor. No load power factor. The cos of phi 0 is called no load power factor, and primary induced EMF E1 is of same magnitude but opposite phase with the V1. That means as per the Lenz's law, E1 and E2 are exactly anti-phase with the V1 because of the Lenz's law. Last lecture we discussed about the Lenz's law. This Lenz's law opposes the cause behind produced. That means V1 and E2 always opposed to the V1. Okay. Then by using this phasor diagram, we conclude that the no load current I0 is equals to the no load current I0 equals to IC plus IM. No load current I0 equals to IC plus IM, and core loss component IC equals to no loss component IC equals to I0 sine of phi 0. I0 cos of phi 0, and the IC equals to IM equals to I0 sine of phi 0, and the power factor cos of phi 0 equals to IC upon I0. Okay, so in this lecture we discuss on what is meant by ideal transformer on no load. In case of ideal transformer on no load, we consider all the losses but in case of practical transformer on load, we have to consider the losses. In case of ideal, we don't have to consider the losses. After considering the losses, the no load current I0 having two components, IC and IM. The I0 equals to IC plus IM, and IC equals to I0 cos of phi 0, and IM equals to I0 sin of phi 0.